Good afternoon once again. We'll start with where we left. Last time we had discussed a few D2A converters, rather weighted resistor type digital to analog converter. We had discussed, just to recollect what it was. It had, for corresponding to 4 bits, it had 4 switches, and we had 4 steps of resistances. First step corresponding to R, second step corresponding to R by 2, third step corresponding to R by 4, and fourth step corresponding to R by 8. The resistances were divided by half at each stage. So the weightage was varying at each stage of the reference voltage, and we converted those digital signals into analog equivalent signals. The problem we cited in case of weighted resistor type D2A converter was that selection of resistances was very critical. Whatever conversion I want to get corresponding to conversion of a given digital signal into correct analog signal, the calculation of resistances was a tricky part. Now the second type, that is R2r Ladder DAC. In this type of DAC or digital to analog converter, that problem of selection of appropriate resistances is sorted out to some extent. If you look at the circuit, now this is our familiar op-amp circuit. As you can see, you have the non-inverting terminal which is grounded, and the inverting terminal is provided with the reference voltage. Now this reference voltage, now this is the feedback. Now this should be very clear. Your op-amp doesn't come all alone. It will always have a feedback loop. Wherever you use your op-amp, in whatever form you use your op-amp, whether you use it as summer, subtractor, multiplier, integrator, differentiator, whatever it is, one feedback loop. So this is the standardized notation for, or symbol for your op-amp. Remember that. So that output is fed back, and this op-amp will be used either as a voltage follower or a summer or a subtractor, or whatever role it has, or comparator, whatever role it has to play. Okay, so this part is my op-amp, and at the inverting terminal, I have 4 stages. Okay, stage 1, stage 2, stage 3, stage 4. Okay, so and at each stage I have resistance 2R, 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 and you have R, R, R at the 3 stages. So that is why it is called as R2R type of a ladder. Now ladder, if you see from this side, it looks like a ladder. It doesn't matter whether I draw it from left to right or whether I draw it from top to bottom. It remains as similar to a ladder. The look remains similar to ladder. And I am providing the reference voltage. Just be a bit attentive. Whatever reference voltage I am selecting, okay, now that reference voltage I can decide based on the range of digital to analog conversion, because that reference voltage, depending on the resistance you have selected, whether you selected R, whether you selected R2R, or whether you selected R2R, depending on that, this resistance will affect the input given to my op-amp. Remember, op-amp receives only analog signals only, remember. So whatever voltage I am going to give to my inverting terminal of op-amp, that will be dependent on the resistance it is covering, remember. Now, which step of the ladder or which steps of the ladder will be picked up for conversion? Please be attentive. What steps? These are the steps of the ladder. These are also called as rungs. In PLC terminology, it is called as rungs. Rungs of the ladder or steps of the ladder. How many steps I'll be using out of this resistance ladder will be dependent upon my binary digit. Okay. Now my binary digit, if it has got 1 0 0 0, if it's a 4-bit number, 4-bit word, 1 0 0 0. What is there? There is one electronically operated switch is there. Just see here. There is one electronically operated switch. Once the switch, if number 1 is there, this switch will bring this branch of reference voltage into action. Okay. So that much voltage will be supplied to my inverting terminal. And remaining, as I said, my number is 1 0 0 0. So remaining zeros. So this switch will be in 0. This switch will also be 0. This switch will also be 0. So that voltage, remaining voltage will be grounded. Remaining voltage will be grounded. Remaining voltage will be grounded because this corresponds to 1 0 0 0. So 1 means this switch will be operated, and whatever is the reference voltage corresponding to my 2R resistance, that will be applied to my inverting terminal of op-amp. Okay. So, and remaining will be shifted to 0. So there will not be any impressed voltage as such. There will not be any impressed voltage as such, as you can see. So this will be my equivalent representation of the analog signal. Just for an example, let us say my number is 1 0 0 0. Okay. So what that number corresponds to? If you remember, rightmost or least significant digit corresponds to 2 to the power 0. Second, 2 to the power 1. Third, 2 to the power 2. Fourth, 2 to the power 3. 0, 1, 2, 3. So first 3 from right are 0. And the last one is 1. So 1 is 2 to the power 3. My number, decimal number, is around 8. Okay. So that number, just as an example I am telling you, that equivalent voltage I should be able to provide here at my voltage follower. Now this voltage follower, whatever the non-inverting terminal is grounded, as I am calling this as a voltage follower, what function this voltage follower has, it buffers the value that is inputted, plus it transmits the value as it is at the output. So 8 volt corresponding to say 1 0 0 0. The same 8 volt, which is the analog signal corresponding to digital bit or a binary word called 1 0 0 0, will be converted into 8 volt, and that will be supplied here, and this op-amp being a voltage follower will just forward this signal as the output. So this is how my digital signal is converted into equivalent analog signal. Let us quickly see what is the description. Just the problem with weighted resistor network is that accurate resistances have to be used for each of the resistors, and it is difficult to obtain such resistors over a wide range needed. Maybe that in weighted resistor type, for some numbers, for 4-bit word, I can work out various resistances. If I have got varieties of digital inputs, I cannot modify those resistance values every now and then. As a result, this form of DAC, this form means weighted resistor type, DAC tends to be limited to 4-bit conversions. Another more commonly used version uses R2r Ladder Network. Just now we discussed that. This overcomes the problem of obtaining accurate resistances over a wide range of values. Only 2 values are required. Just one example of 8 volt DC I just showed you. So accordingly, depending on my range of values, I can select appropriate R2R values, and so that my D2A conversion will be taking place smoothly. I did not decide for the range of values. I did not decide what should be the R value for each of the digital word. Okay, which will be the case for weighted resistor type. Once I design my circuit for R and 2R values, that should be valid for all the ranges of the values of my digital word. The output voltage is generated by switching sections of the ladder to either a reference voltage or 0 volt, according to whether there is a 1 or 0 in the digital input. That's what we discussed. Either I'll be applying reference voltage to my inverting terminal, or I'll be applying, if the switch is in this position, it will be applying 0 volt because there will not be any voltage supply. Okay, that is what this last sentence means. So this is how both these D2A converters can be used for digital to analog signal conversion. Remember, so we are into the chapter of signal conversion. It is a bit prolonged chapter, so many electronic circuitries we need to study and remember. Okay, we'll move further for both these analog to digital conversion. Remember, friends, particularly in case of analog to digital converters, A to D converters, there is a big problem always that if I'm receiving one analog signal and that analog signal is to be converted into digital form, whether I should refer to a continuously varying analog signal or whether I should take a sample of that analog signal and then convert it into a digital form. Now, this second case is the practical case wherein the analog signal is sampled or a sample of analog signal is taken that is converted into digital form, right? Though I am telling you slowly, but the sampling and conversion time, it runs into microseconds as we discussed in ADCs, isn't it? So microseconds, we don't even feel that it is sampled and it is converting. Okay, sampling, holding and converting. So that sample and hold circuit will just go through and understand what is this sample and hold amplifier. This is once again operational amplifier. As you can see, the non-inverting terminal is supplied with a capacitor and then it is grounded, and the inverting terminal you are providing a feedback. Then to my non-inverting terminal, I am providing the analog signal input. Okay, analog signal input, I have a control over a switch. Okay, now this also is automatically generated. This sampling time, that also can be decided, and automatically this sample and hold amplifier will be put on or put off, will be switched on or switched off. So that sampling frequency also I can decide. The sampling time also I can decide. As I said, it runs into microseconds, and accordingly I sample the signal and then hold the signal and then transmit the signal. So what for it is required? It is mainly used in my A to D converters. Now what happens here? Now when this switch is off, there is no signal, so no output. Suppose I am giving some analog signal, maybe 3 volt DC. I want to convert it into digital form. My A to D converter will come later on. We are just talking about sampling and holding amplifier. Okay, we already discussed how the A to D converter works. Okay, so beyond that, my A to D converter will be there. Now, when I'm supplying this analog signal, let us say 3 volt. So my ADC, whose sampling frequency and sampling time is preset, accordingly, this switch will be put on. What will happen? This 3 volt will be supplied. Now that whatever is the current flowing, that will be stored by my capacitance in the form of a charge. Okay, so that will be stored, and then when this switch is put off, that means this 3 volt is no longer applied. Remember, already applied 3 volt and corresponding current is already flowing. Now that is stored by my capacitor, and now once this switch is put off, now this capacitance will start discharging whatever is the current, whatever is the stored charge, which is obviously equivalent to my 3 volt voltage. Now this will start discharging, and this voltage follower will transmit the signal, through my op-amp as the output. Okay, and that the analog signal will be converted to digital form, and as I said, this on and off time of this switch, it runs into maybe 2 to 4 microseconds. So one lot I have completed. Once again, this will be put on. Once again, 3 volt or whatever is the next voltage, maybe 4 volt is applied. That is a continuously varying voltage. 4 volt is applied. Then that will be stored in my capacitor. Then it will be removed so that that signal will be held, so to say, sampled for certain duration of time, so that the charge, the capacitor is charged. Then removed or put the switch off so that the signal is held and it will start discharging, and then I'll be having conversion part. This is how my sample and hold amplifier works. So let us quickly see. It takes a finite time, just be attentive. It takes a finite time for an ADC to convert an analog signal to digital form. And problems can arise if the analog signal changes during the conversion time. If the signal is continuously changing at a faster rate, whether my digital converter will be able to cope up with that. Yes, it can cope up with that, provided my sampling frequency has to be higher. My sampling and holding time has to be low, right? So accordingly, I can set. To overcome this, a sample and hold system is used to sample the analog signal and hold it while the conversion takes place. Now, let there be variation on the input side. I don't bother. Presently, I have sampled a signal. I'll be converting, I'll be sampling, I'll be holding, and then I'll be converting. And as I said, it will not be taking minutes, so that the voltage has already changed a lot and then my digitization takes place. No, this sampling and holding time is also running into microseconds. This switching up happens and sampling happens so fast that we usually don't even realize that sampling and holding has happened and then the conversion has happened. Okay, but this is required. To overcome this, a sample and hold system is used to sample the analog signal and hold it while the conversion takes place. Now, the basic circuit consists of an electronic switch to take the sample with a capacitor for the hold. For taking the sample, there is a switch. For holding the signal, there is a capacitor and an operational amplifier as a voltage follower for transmitting the signal. Voltage follower, it follows the input voltage. The output follows the input voltage through an op-amp. That is called as a op-amp as a voltage follower. Now, the electronic switch is controlled so that the sample is taken at the instant dictated by the control input that I can preset. When the switch closes, the input voltage is applied across the capacitor and the output voltage becomes the same as the input voltage when the switch is put on. If the input voltage changes while the switch is closed, the voltage across the capacitor and the output voltage change accordingly. When the switch opens, the capacitor retains its charge. The capacitor retains its charge. The switch is now open. The capacitor retains its charge and the output voltage remains equal to the input voltage at the instant the switch was opened. The switch जरी open झालं, just moment आधी जेवढं voltage होतं तेवढं voltage तुमचं किंवा तेवढं signal तुमचं राहणार, because that voltage or that current will be stored in the form of charge in the capacitor, and that it will release the equivalent value. The voltage is thus held until such time as the switch closes again. The open and close kadi hona, we can decide it and we can set it. The time required for the capacitor to charge to a new sample of the input analog voltage is called the acquisition time. The time required for the capacitor to charge to a new sample of the input analog voltage is called the acquisition time and depends on the value of the capacitance and the circuit resistance when the switch is on. Typical values are of the order of, the acquisition time values are of the order of 4 microseconds. 4 microseconds. Okay, so a millionth part you can say. Millisecond म्हणजे किती? 1000th part of a second. Microsecond, 10 to the power -6 the part of the second. So it's so fast. That's what it is. So this is how my sample and hold amplifier, or op-amp as a sample and hold amplifier. So this might be there as a note, might be asked in the exam. So we should be able to draw this circuit. We should be able to draw this circuit, and then we should be able to explain sample and hold amplifier. Okay, we'll go a bit further. We'll go to the, well, I forgot to go into slideshow. Multiplexer we should study. Okay. Okay. So this is multiplexer. Now we are talking about the signal conditioning devices. As you can see in the block diagram, multiplexers. Now what is the function of multiplexers? Remember, we have seen the various signal conditioning devices. We have seen amplifiers, we have seen comparators, we have seen summers, we have seen filters, we have seen A to D converters, we have seen D to A converters, different types of input signal conditioning devices we have seen. Now let us see if I have got more than one signal that is to be processed. Supposing that I have a robo, multi-axis robo is there, wherein I want to control the angle of links also. I want to control the opening and closing of the gripper also. I want to have a vision sensor also to see the object. Then I want to control the motion of the entire vehicle also. So 3-4 signals, maybe one corresponding to distance, one corresponding to pressure, one corresponding to gripping force. So 3-4 signals are there, and those signals are, let us say, some are analog signals, some are digital signals, and these are to be processed appropriately conditioned through my signal conditioning devices. Okay, so can we afford to have separate A to D ADC? Can we afford to have a separate filter? So separate devices for separate signals, it will become very costly affair. So what is done is, I have a single A to D converter. I'll be having storage register, single storage registers. But what I do is, I take various signals sensed by the sensors and transducers, one after the other. So to say, if you remember in heat transfer lab, whatever was the experiment, maybe thermal conductivity of a powder experiment was there, or composite wall experiment was there. So there were different thermocouples, those were used, isn't it? So, but there was only one signal conditioning device. You used a toggle switch. Pahila thermocouple, dusra thermocouple used to toggle and used to measure the temperature. And that analog signal was getting converted. For that switching position, I used to get the converted signal in digital form. So this sort of toggling, which we did mechanically there, in case of heat transfer equipment, this multiplexer will do it automatically. So it will keep on receiving number of signals from sensors and transducers. It will receive, and then it will process and convert it into digital form as per the requirement. The multiplexing device or a multiplexer receives a number of signals, but it processes it one by one. So I don't need separate ADC for each signal. I can have a common ADC on many common devices, and then through multiplexing, one by one, I can process those signals. So this channel select signal can be automatically controlled. So the multiplexer will select which channel. Channel 2, I want to convert it into digital form, and I want to read. So accordingly, the multiplexer will select the channel and process that signal. Channel 3, let us say channel 1, channel 2, channel 3, channel 4, corresponding to 4 different sensors and transducers. So accordingly, my multiplexer will select that signal from the sensor and transducer, and then that signal is sampled, held, and converted by ADC, and I get a digital output. This is how my multiplexer works. Let us quickly see. A multiplexer is a circuit that is able to have inputs of data from a number of sources, and then by selecting an input channel, give an output from just one of them. Just now I discussed. In applications where there is a need for measurements to be made at a number of different locations, rather than using separate ADC and a microprocessor for each measurement, a multiplexer can be used to select each input in turn and switch it through a single ADC and microprocessor. The multiplexer is essentially an electronic switching device which enables each of the inputs to be sampled in turn. The transition time between taking samples is 0.6 microseconds. So we don't even sense it. It happens so fast. So friends, we'll stop for today.